be starting this course. Welcome to Programming Language Pragmatics. Actually, this course is programming language, the CPSC 46K. My name is Eric Chou. I will be the instructor for this course. First, I would like to say thank you and welcome you to come to this class. And I know most of you maybe will be watching the recorded session, but it's okay. And I will get started right now. First, I would like to give a short introduction for myself. My name is Eric Chou, and I graduated from National Taiwan University in Taipei, Taiwan in 1990s. I majored in computer science and engineering, and I actually took a lot of courses in this university. And then I got my master's degree and PhD degree in University of Southern California in Los Angeles. And my main research topic is VLSI, sensory information processing. That is working on the sensor, all kinds of sensors, including the image sensor, the communication sensor, the vibration sensor, the capacitive sensor, all types of sensors, and doing the information capturing and the vision recognition and all sorts of processing afterward. So I have the charged spirit of the USC. And currently, I'm a IEEE senior member. Is the Institute of the Electrical and Electronic Engineers. And I grew up from at Taiwan, and the country is famous for the boba tea. And I'm an inventor, and I am a researcher, and I am an engineer. So I work on a lot of engineering work before. I will introduce that later. Currently, I live in Fremont, California. I have been in this city for 25 years so far. I'm sorry, 21 years. And actually, this city is the city I lived for the longest time, even longer than my hometown that I grew up at. Actually, I only lived there about 18 years. And Fremont is located in San Francisco Bay Area. It's on the East Bay right here. And we are on 880, 680 right here. And then as you can see, the Fremont is the capital of the electrical car. Tesla is located over there. This is the freeway 880, and Tesla has a lot of robots to do the manufacturing of the electrical car, and they are quite successful for doing that. And this factory, it used to be the GM factory, and about maybe 20 years ago, they sold it to Toyota. So it has been a Toyota factory for certain maybe 20, 15 years. After that, Tesla took over maybe about 5 years ago. And they have been quite successful over there. So whatever S model, any X model, whatever model they have is coming from this factory. And they built a giant battery factory in Reno, Nevada. And the Highway 80 is where they test their car. They have all the electrical station to charge the car up. So Silicon Valley is full of all kind of opportunities. On the East Bay, we are more focused on this sort of manufacturing, but high-tech manufacturing. South Bay used to be the center for silicon industry, like Sony, Samsung, and all different semiconductors company are located over there. But they have moved out of Bay Area already. So now a lot of company on social media or software actually more on the West Bay, that is on the Highway 101, and to this South Bay, Sunny Bay or Mountain View area. And in San Francisco City, it's more related to software in the website industry, and also related to financial sector. And I grew up from at Taiwan, and Taiwan is famous for quite a lot of things, like a boba tea, as I just mentioned. And there are two companies I would like to introduce to you. They are very important in the computer industry. The first one is the Taiwan Semiconductor Manufacturing Company. And as you can see right here, the Apple iPhone using A9, A10 processor. TSMC is the manufacturing for these chips. So you may have been using a lot of gadget like cell phone, iPad, or those kind of things. You would be using their chip. In fact, a lot of not only this Apple processor, but also the Wi-Fi chips from Broadcom or your cell phone communication channel by Qualcomm. They are all manufactured by TSMC. And as you can see right here, it's a wafer. Actually, this wafer would have a lot of chip right here. Each one is an individual chip. And then after that, they will cut it into several die. Each of these small square type things is called a die. And then they do some packaging on it. And after packaging, it will be something like this A10 chip. But the die actually about maybe only 1/10 of the size you see over here, because the packaging including a lot of I/O pad, and those I/O pad solder to the PC board, and you have and by doing that you connect your processor to your cell phone board, and that board will connect it to the microphone or different devices that you have on your cell phone. So TSMC is the heart of is manufacturing the heart of your cell phones and computers. Another company that is famous for Taiwan is Foxconn. But right now, most of the manufacturing facility for Foxconn is in China. And as you can see, this person is handling the iPhone 6 or iPhone 7 right here. And as you can see, this is a production line they have. This company hire around 1 million people in China to do cell phone. And ironically, each individual person sitting here, they work like a chicken, sucking an egg every day. But actually, their pay is extremely low. Their monthly salary maybe still cannot buy a iPhone 7. That is about maybe $700-800, but their salary maybe just 2,000 RMB or 3,000 RMB converted to US dollar. That would be only $500 or $600. So, and they have supervisors standing right there watching what they are doing. So this production line is very busy, but very productive. But these people get very low pay. But about 85% of the iPhone production line is done by this company, so it's quite important. And for myself, as I said, I'm an engineer and an inventor. So I would just briefly go over the invention I have. Right here, I have a PCT that is a worldwide, WO is worldwide patent for multimedia accessible universal input device. So it's related to some cell phone-like device. That's my invention. And I also work on the cell phone input system for different language, including Chinese, Korean, Japanese, English, Spanish, all kind of different language, more than 20 different languages. So language is power, and you are here for the programming language. It is quite important, not only the programming language, but also the natural language. Both of them are very important, and if you know a lot of them, you will be able to communicate with different people, and you will be able to work on different type of project. And that's the purpose you come here, to pick up more language and know about how to design a language and to implement a language and how to use a language. And right here is another pattern on amorphous silicon active pixel. So it's an image pixel. On image pixel, I have 4 patterns, and this one is US pattern. And I have the hexagonal grid for the sensors and use amorphous silicon. Amorphous actually means liquid type silicon. So as you can see, my invention covers the semiconductor and also software industry. You can call me Mr. Everything, but I just try to do whatever I know and try to keep inventing. And this is another invention I have, that is a measure and apparatus for delay adjustment for channel recording in baseband communication receiving system. And this one is used for hard disk reading channel and also for Ethernet. And the purpose I do that is for Ethernet. And this is on Microwave Semiconductor. And this company actually was acquired by some other company already. So if you try to find this company, it's gone already. And this, again, this is another US patent. And I have more patent right here. And I also have one patent, a couple of patents that's registered in Taiwan. And this one is registered in Europe. The patent code EP is for Europe. And I started my first job at the Hewlett-Packard and with Hewlett-Packard Lab. And Hewlett-Packard is said to be the origin of Silicon Valley. And Silicon Valley's pioneering spirit started from Hewlett and Packard, Mr. Hewlett and Mr. Packard, starting from their garage. So the Palo Alto City keep their garage as the origin of the Silicon Valley. And right here is another invention. It's a European patent. And this is my wife. Her name is Christina Chou, and she is a project lead in Synopsys Inc. And Synopsys is a EDA company, and that company is actually very much related to programming language, because you need to have the try to convert the system C into register transfer level languages, and such as Verilog or VHDL, and those language again being synthesized into gate level description, and gate level description will be synthesized to physical layout, and they do timing model, all sort of things. So in the EDA industry, there are several levels of language translation, and this company is a good company if you, sorry for the interrupt, and if you know about programming language, this company do need a lot of engineers who know the theory of programming language. And she likes cooking, and all of this is her product. And this one is my elder son. He won the Pan American open gold medal. And this year he's applying to college. He admitted to UC Irvine, UC Santa Cruz, Texas A&M, these different research type university. He waitlisted by University of Washington, University of Wisconsin, Purdue University, but he got denied by UIUC. Actually, I like him to go to Urbana-Champaign, but somehow he actually spent too much time on Taekwondo in the ninth grade. So his GPA in ninth grade is not good enough. That's why he got waitlisted by these different university and got denied by Urbana-Champaign. But anyway, he is heading for a research university. Maybe he will pick from Irvine or Texas A&M. And this one is my younger son. His name is Christopher Chou. He's a straight A student and national champion. As you can see, he competed in Chicago and won a gold medal and a silver medal over there for Taekwondo. And Chicago is a lucky place for him. And these are them when they are very little, go to the Legoland. And recently he won the 2016 bronze medal from AAU Taekwondo at Florida, Fort Lauderdale in Florida. Now, the second thing I would like to talk about will be the syllabus for this course. Here, I'd like to talk about the syllabus. First, I would like to talk about how this course is organized. And because it is a 8-week course, so it is quite short and quite intensive. So you need to be prepared that each week you probably need to spend 15 to 20 hours on this course. And that's the way it is. Normally, this is a 14 to 16 week type of course. Then you probably spend about 5 to 6 hours a week. I'm sorry, maybe 10 hours a week. I'm sorry, but because it is so intensive, so you need to be prepared that you have to be spending more time on this course each week. And this week, this course, we are based on a textbook, and you will see that in the textbook section in your Blackboard system. But right here, I just briefly go over the organization of this course. The Unit 1 is teaching you the fundamentals. So basically, the fundamental of the programming language will be talking about how can you design a programming language and implement it. That's the topic we will cover. So chapter 1, we are trying to introduce different type of programming language and also talking about their difference. And chapter 2 to chapter 5 is talking about different phases of a compiler or interpreter. So we starting from chapter 2 on the syntax, and chapter 3 for data type checking, and chapter 4 we are on semantics analysis, and chapter 5 we are on code generation or target machine. And this chapter 2, 3, 4, 5 are considered the design of compiler and implementation of compiler. So this part actually is the core of this course. So right here you feel more tension and it is more difficult on this part. And if we move on to the second part, the part Unit 2, the core language features, including the control structure and the data structure. And the control structure is on the different type of control, like decision, selection, iteration, and recursion. And chapter 6 is on if, then, else statement, switch statement, for loop, do while loop and while loop. So basically, chapter 6 on the iteration and decision making and selection. And chapter 9 is on function or subroutine or member methods. So these two, chapter 6 and 9, are basically on the control structure. Chapter 7 and 8 on data types. So chapter 7 on data type checking, chapter 8 on composite data type, and these two actually on data. Chapter 10 is on object-oriented programming. Object-oriented programming is a new paradigm. It includes the control structure and also the data structure. So you can see this chapter 10 as a summary for these two parts, and it will conclude the unit 2. And unit 3 is on programming paradigm that including the logic programming, functional programming, and logic programming, different type of programming, and also the concurrent programming. But we will only pick number 13, the concurrent programming, because this chapter covers the concurrent programming, parallel programming, it's more related to the object-oriented programming. And the logic programming, functional programming, those functional programming, these different paradigms actually are of different machine types. So pretty much it doesn't actually relate to our main topic too much. So they will be omitted because we don't have that much time. Unit 4 is on programming environment, including hardware and software environment. But again, we don't have that much time to cover chapter 15, 16, and 17. So with these different chapters, I would say you will build up a strong knowledge for how a language is invented, how it is created, and how it's designed and implemented, and how can you pick a language. That's the purpose of this course. And for the grading part, we use a accumulated point system, and it is quite easy. For each assignment, you will be assigned by a certain point, maybe a basic point and bonus point. And at the end of the semester, we will sum up all of your basic point and bonus point, and you will have two numbers. One is your total base point and total bonus point, and that will sum up as your total point. And then this total point will be divided by the maximum base point that a student can get. So by dividing that, you will get a percentage score, and we use the percentage score to decide your course grade. And your total point may be higher than the maximum, but you will be kept. And that's okay, but I'm trying to be nice to everybody, but I expect everybody to work hard to earn the point that you deserve, but I will try my best to be nice. And right here is a rundown for the different projects we have right here. And maybe in the middle, we would add something, but roughly this will be what you have. And the total maximum point available right now is 2255. And then these are the base point for each individual assignments. And at the end, you will get some base point and some bonus point on each of the items. We will sum it up, and then that will become your total points. And then these total points will be divided by this number 2255 for the time being, and get your percentage score, and then we'll use that to determine your final grade for this course. And right here, I would like to show you how this programming language course is connected to other courses in computer science. And as you can see right here, programming language is in the center of computer science. And when you are in lower division of computer science department, actually you have C, C++, Java 1, Java 2, those type of course. And then you move on to sophomore, you learn data structure or algorithm or combined course. And this course is the following course for data structure and algorithm. So I'm expecting you have some knowledge of this and some programming experience. Either you know Java or C++ or C, that would be our prerequisite. But don't worry if you only have one part of it, because not everyone knows everything. It's okay. And Java and C, they are core in the C language family. So if you know one part of it, you will be able to pick up the other part quite quickly. That's okay. No, that's nothing wrong, and you will be fine. But in this course, you need to be prepared that you need to pick up a lot of programming language. That's the purpose that you come to this course. And you need to be able to switch language in a very short time. And that's the training you want to have so that you can survive when you are assigned some programming task. And after this programming language course, you are encouraged to take the compiler design, and that is the lab or the following implementation course for the programming language. And as I say, the compiler design and concept part is the core for this programming language course. But in this course, we only talk about the theory or what it is. But about the implementation and how to do it, you have to take this compiler design course. So I use a darker brown color for it. And nearby, you have the hardware track, you have the system track courses, you have the theory track courses, and all of these are related to this programming language, and I will introduce this later. But the hardware side, you need to learn assembly language, that's part of the programming language. You need to know about computer organization for register transfer level language. And you need to know about computer architecture for instruction set architecture. And microprocessor lab is very much recommended for the computer science and engineering student, but I know normally it is not required for computer science only student. So I'm not sure whether this is offered at Lewis or not, but anyway, that's the lab for this computer architecture and computer organization. You will have the chance to build a PC board or write some assembly code for it. So this course is also very important. And from the theory side, we strongly cover the automata and the finite state machine. And computation theory will be the most advanced course in this track. You need some knowledge about logic design because you will need to know about some of the selection or evaluation for the logics. And these knowledge are very important for programming language as well. And from system side, you need to some university may offer the Unix scripting, but not a lot of university have this. But scripting is very important because scripting is usually based on the operation system shell, and the operation system shell usually is a interpreter itself. And for the operation system theory, actually you need to pick up the scheduling topic. And the scheduling is very important for concurrent programming part. So it is also related to the programming language. And again, the Unix or operation system lab is very important, but I'm not sure whether it's offered by Lewis or not. But this is how this programming language is related to different courses. Basically, you need to know about data structure, ISA, the instruction set architecture, automata, finite state machine, operation system, the scheduling, and you also need to know about some programming language. So actually, it's a combination of all of these different knowledge toward a very complicated software called compiler. And that's the purpose for this course. Is actually a kind of review for a lot of topics and also help you to be able to determine how to implement a language or to pick a language. And the last one, you may download the PDF file. I don't want to go into there too much, but this one helps you to pick a programming language for certain application. So this is the end for our syllabus. Next, I'm going to talk about the textbook. The textbook that we would like to use is the Programming Language Pragmatic, 4th edition, done by Professor Michael L. Scott. He is a famous researcher in this field, and his book is quite famous. That's why it has already 4 editions, and these are the cover for the previous editions. And he's teaching his own course on programming language design and implementation. And we use this textbook, but we don't follow it 100%. As I said, some chapters are omitted because it's too long for us for this textbook. That's really too long. And also some of the hardware part, he doesn't describe exactly in the right term because he's not really a hardware person. And some of the data are actually outdated. I just update to match the current programming language situation. So, but this book is actually quite a good book for programming language. The word programmatic is actually related to mechanism. So basically, we are teaching you the mechanism for programming languages. You need to understand how it works and how people make it work. That's why we call this book is called Programming Language Pragmatic. You need to know about the mechanism and need to be able to design it, implement it, and use it. And there's a companion website right here for you. You can check and you will be able to find some information over there. The next topic I would like to talk about is how to proceed in this course. And right here, this is how the book and the blackboard are organized, all the materials. So as you may see, that I give you a lot of information and links and all sorts of things. And this page will help you to organize everything. First, you need to read your textbook by yourself. So this textbook is pretty much a must. And that will help you to understand a lot of things. And you need to read it before each of the lectures. And then when you come to my recording session or live session, you should have some knowledge already. Then you don't waste your time in the lecture. You know, if we are moving on too fast, say, because this one is a 8-week course. So I want you to pre-read some chapters every week. And about what to read, you should actually look at the Blackboard system. I will show you the Blackboard system later. And on each week, I will assign some language installation and some lab. And it is impossible to learn the language in 1 week. But why we are doing this? That's because that I want you to be able to switch language pretty fast and know where to find the related information. And this training is very important that you will be able to survive in the fast-paced industry, programming industry. So you need to learn how to install the software and also bring yourself up, like be able to do some simple programming in a very short time. And that is the purpose for this training. And also there are some lab that you need to work on. So, but if you want to run some example program, but you have not installed your software on the week, you can jump to different chapters, different week to find the information, to watch the video, so that you will be able to install the software before the week comes. And in each week, we also give you many example programs, and those programs actually are in the textbook. So you actually need to download a language compiler or interpreter and also run those programs. And by doing that, you will be able to understand this textbook much better. And with this knowledge, you will be able to handle the term project. And I will encourage you to start your term project from day one. So starting from today, you need to work on the term project. And the term project is the only big project you will have on this course. And in week 3, you need to turn in the term project proposal. You need to let me know what you want to do in the term project. But we give you 3 options for the term project. So you need to watch the term project section in the Blackboard on the course menu. You should be able to find those term project options. And I encourage you to start from day 1 and work till the last day, so you will be able to have a good project. And the purpose for doing this term project is actually to help you to handle a project from the idea to deliver some software. And the week 3 report, I will need you to write down what you want to achieve. So when you go to the real job, you will be able to write some project proposal. You do some feasibility study, some early planning for the project, and then you need to be able to write some project proposal. And at the end of the project, I want you to work on a presentation, either in PowerPoint format or you tape yourself on a video. That is very much encouraged. And also including your coding and all whatever you have done in the project, put into a zip file as your submission for term project. And the purpose for doing that is you need to start your term project from idea to implementation, and all the 3 options are related to programming language, and the purpose is to help you to learn the knowledge to handle the project in the industry. And this part is about the programming side. About the reading side and knowledge acquisition side, they are extra reading and material and links. You don't need to finish all of the links, but you are encouraged to try as much as possible. After reading the book and the extra material, you should take the quiz. The quiz will give you some quick idea of which part you need to learn more. And after that, you need to work on the homework. But homework is a little bit more difficult, so you need to take quiz first, and then you work on your homework. And homework will cover some topic that is not available in project and quiz. So about the language installation, week 1, I will need you to install the code blocks for C, C++, that's for GNU C, C++, GCC, And also it includes a IDE, the editor and compiler setup. Week 2 will be on Java and C#. And that is, these 4 languages are the C family language. And these are very essential. It's very important because C family language is the main language we are using for this whole course. And week 3, we are on Java standalone compiler and Python and Eclipse. So this will bring you to another level to use more complicated cross-language, cross-platform IDE with Eclipse. In week 2, we also use the Visual Studio, but I do not give you enough, too much information about the Visual Studio. In this course, we more focus on the Eclipse. And in week 3, you will be learning the cross-language, cross-platform IDE environment. And also, we will also include the first functional language, Haskell. And then that's the week 3. And week 4, we are on the Prolog and the assembly language. And in fact, that's related to chapter 5 and chapter 6. And week 5, we are on Ada. Ada is a concurrent language. I'll talk about these different languages later. Week 6 is on OCaml and also on Scheme. But Scheme now have been changed to a name called Rocket. So actually, this is a Rocket language. But if you see the Dr. Rocket or Rocket language, don't be surprised. It is the language that you know in the textbook. It is called Scheme, so don't be surprised. Chapter 7, we are on JavaScript. Even though JavaScript is not heavy in our textbook, but I think it is quite important to know about JavaScript. Its popularity is gaining, and you cannot ignore it. Week 8, we are on the installation for Scala language, and Scala is gaining a lot of attention now, and it is a functional language. It is also a object-oriented language, and it is a domain-specific language. So it represents many features for future language. So as you can see, I try to organize a whole pack of different language to let you know more about language. And that is why this course is very intensive. Each week you need to work on a lot of things, reading the textbook, doing the lab, install the language, and then take the quiz and homework. And you also need to work on the term project. So it's quite busy, but I try to be nice on grading, but I hope that you will learn a lot from this course. If there are certain things that you feel is missing or misinterpreted, or somehow you think that I need to improve somehow, please let me know. But I would try to provide a very intensive, very comprehensive course on programming language. And the goal is to make you great again. I know a lot of you is jumping in from different career paths for computer science. And my goal is to make you feel great for yourself. Learn how language are created, designed, and implemented. Learn structures, that's mechanism for programming language. Learn new language in a short time so you can switch language very quick. And be prepared for job interview as a developer. Not a supporting role, but I want you to become a good developer. And I know this is only one course and it is short, so the goal is huge, but we are trying the best to give you a lot of information. You may not be able to finish all of them, but you are welcome to download them, and you are welcome to bookmark all of the links, so you can later after the course, you can still find enough information for the whole life, for the whole career that you have that lie ahead of you as a developer or programmer. So I finished this how to proceed for this course. Let me check how many people are here now. Okay, I see Brendan right here. Let me say hello to him. Hello. Do you hear me? I have keep talking about, okay, thank you. I keep talking about 45 minutes. I try to have some break right now. But so far, are you okay with all of the material I covered so far? Okay, thank you. Now I'm going to continue on the next topic. The next topic will be, we will start the chapter 1. Do you have any questions so far? Okay, thank you. Now we are moving on to chapter 1. Chapter 1 is introduction to programming language. Introduction. So it's an introduction for the whole course. Okay. And the first lecture is introduction to programming language. It will be the introduction for the chapter 1. So let's get started. This first slide, you will see the programming language. As you can see right here, JavaScript is so big. And then you will see the second largest one, maybe Java, then Python, and Delphi, and then C#, Bash, PHP, SQL, Ruby, Objective-C, Swift, Scala, Haskell, something like this, okay? Why JavaScript is so big right here? Because they are not weighing this by the number of programmers or the popularity of the language. They are making JavaScript so big because of the number of installation for each language. Why JavaScript is so big is because there are so many websites, and most of the website is constructed by HTML, CSS, the style sheet, and also the JavaScript for the behavioral model. So that's why JavaScript programming is so important nowadays. It is not only used for the client-side programming, but also the server side. So and even a lot of desktop software, they try to incorporate some JavaScript now, and that's why it's so big. And Java used to be very big, and it is still the best language to learn for educational purpose. It used to be very big. It is done for the server-side programming and client-side programming as well, but the client-side being replaced by JavaScript, and a lot of browsers no longer support Java applets. On the server side, it used to have PHP as the largest language in server side. Right now, it's still occupying about 85 or 80% of the market, and JavaScript right now is gaining on the server side because of its simplicity. And you may have heard of the Node.js. That is, it's actually for server side, but JavaScript used to be used only for the client side, and that's why it's becoming more and more important right now. And Java right now, the most strongest supporter for Java is actually Android for the cell phone. it will remain to be strong for quite many years, but as I predict, it will slowly tuning down. It's okay, but Java still be the best language to learn as the first language or the main language to learn, because Java has the most educational material than any of the other language. And Python is also gaining importance. Python and its cousins, say, let me see, R language and also Ruby. Where is Ruby? Ruby is right here. R and Ruby, PR, okay? R is following P. These two R language actually are maybe you can call it as a dialect or a descendant language for Python. And these three language combined with MATLAB, those type of language are used usually for numerical or the scientific analysis or machine learning. If you look at a lot of universities doing machine learning, is actually using Python or Python descendant language, and it's gaining importance. And right now, as far as I know, maybe around 30% of the university is using Python as the first language, and Java is used for AP computer science. So these two languages actually are considered the best educational language right now. And the term I use for educational language is like, you have you cannot learn all the language in one day. It's not possible. But the best way to learn a programming language is actually you play heavy on the first language you have. Say, when I grew up, I speak Mandarin. So I use that to learn a lot of knowledge on the language. That's your first language that you pick up. But later I pick up English. It doesn't matter, but nowadays I use English as my primary language. That's okay. But when you grew up, you need to learn some language as the main language you use. And, pick Java as an example. You learn basic programming idea about the loop, about the subroutine, about the objects, about the class, about the GUI, about the web server framework, about the data collection, like list, queue, and stack, about the data structure, the pointer, reference records. You learn everything on the primary language that you have, the first language you learn, and later it's easy that you use those knowledge to learn some other language like C, C++, or different language right here. So that primary language is very important. And I suggest you, if you want to learn programming language, starting from there. And right here, you see Swift is a scripting language, Object-C, Scala, C++, C, C#. And all of these, we can call it as the C family languages. And it is the most dominating language. Even JavaScript can be considered as a C-like language, even though some data type of the JavaScript is not declared. The data type of JavaScript is not declared because it's a interpreter, more like an interpreter-based language. So the type can be inferred while the program is executed at a dynamic at a runtime. But that's okay. But basically, these are different C family language. That is the most dominating language family right now. The second thing I would like to talk about is the machine language. It's the target language that is run on the machine, and on each machine, actually, as you can see right here, is in binary format, and it's not readable. So we need to translate our high-level language to machine language, and actually, it's not readable. So people rely more on the high-level language. So Assembly language is in between machine language and high-level language. The interface is called assembler. You translate the assembly language to machine language, and the machine language run on your hardware, and the interface is called instruction set. And we call a two processor instruction set compatible. Say AMD x86 processor and Intel processor are compatible by the instruction set. So they write the assembly code in the same way. They can run on Intel processor, and Intel processor may have they have a core, i7 core, i5 core, different core. But those machines have different clock rate, and they also have different memory size, cache size, register profile, different type of the combination for the processor. The die size are different as well. The packaging are used differently, but as long as they are instruction set compatible, that means I look at the machine from the assembly point of view, they are the same. Then we call it is instruction set compatible. And high-level language will be converted to assembly code or directly to machine code. That is the job for compiler or interpreter. We will talk about this later. And that's how these three levels of the language line up. And high-level language is the most readable language. And basically, in the old days, they try to use the plain English as the programming language for high-level language. But actually, plain English has a lot of redundancy. So most language right now look more like C language. You have a lot of brackets, parentheses. That's not actually plain English. Some language like Ada or Pascal, they use begin end, and that actually is more English-like. And this popularity for 2016, as I mentioned, Python and Python family, Ruby and R are getting popular because a lot of people in data science are using it. And this chart is different from the first chart. It's by the preference of the engineer. So Python right now is the most preferred language. And then Java won't die away, but it's slowing down. C, C++, and these two languages combine around 20% for maybe 20, 30 years. And before that, C is dominating in 1970s, 80s, and early 90s, they got knocked out by Java. And C# is I should say, is a clone version of Java by .NET by Microsoft, but it is C-like, but it's gaining importance as well. JavaScript, the preference is not high because it's only for website, but it's gaining its place in the market. And here is the timeline. The first language is Fortran. Fortran is short for formula translator or formula translation, so that's called Fortran. And Fortran is very important, even though it's an old language, but right now still being used by some scientists. And Fortran is important in human history because in the early 68, 70, early 70s, we use Fortran to send human to the moon. So all of the program are on IBM 360 and program in Fortran language. So don't look down for this old language. It is very important, and a lot of scientists are still using it. And after that, we have PL1, programming language 1, programming language 0, but it is not popular for programming language 0, and it's a later version programming language 1 is more popular. And then business use COBOL, but COBOL, there are still a lot of banks using COBOL. And then Algo 60, Algo 60A, And then we move on to first structured programming language called Pascal. Pascal is successful educationally or academically, but it doesn't become a mainstream language in industry. Instead, in the early 70s, 71, Unix system came out, and C language is the primary language that is used to program to develop the Unix system. So when you use Java or you use C++ or C, when you try to get a system time, you always get the January 1st, 1970. That's based on the C language, the default. That's based on the Unix first day for the clock. When they set up the Unix, that's how they set up. And C language later developed into C++ in probably 1985-86 timeframe. And that is the first commercial successful programming language. And C++ is popular for a while, but it has the same problem with C language, that is syntax-wise so complicated. A lot of people cannot actually understand it. It's too low levels in some sense. But these two languages remain a dominating language in device level programming. And early 70s, there is Smalltalk. It's quite a good object-oriented language, but it doesn't become the mainstream in object-oriented programming language. Object-oriented programming become popular because of Java, and it is used for early HTML and website construction, and that is why Java become popular. And then later C# developed based on C++ and Java. And this trend, we call it object-oriented programming language. And this is imperative programming language. But the difference is only that you add the concept of object-oriented programming on it, and actually it is an outer layer for imperative language. And right here, you have concurrent language for modular Ada 83, Ada 95, and now we have Ada 12, 2012. And this remain there, but they never become the mainstream for commercial purpose. They are used, for example, like Ada by the defense people, military purpose. It's quite safe because of its security. And Ada is promoted by DARPA in the early days, but they never become a commercial language. And functional language, we have Lisp. This is very important. Many applications being influenced by Lisp, especially the EDIF language used in semiconductor markup. It's quite useful. And then nowadays we have ML. OCaml is ML language, and then Haskell. But functional language have been there for a while. Never become a mainstream, but it become a domain-specific language. Prolog is based on the rule-based system for logic. Never become popular, but still surviving there. And why there are so many programming languages? There are a few reasons. Evolution, we need to do things better. And then social economical factor, C# came out because of .NET system, because Microsoft don't want to use Java. No, that's my personal opinion. Anyway, that's because some proprietary interest or commercial advantage. And then special purpose, special hardware. You can check this website to find out. And what makes a language successful? I think the number one is very important. Easy to learn. That is very important. That's why nowadays Python becomes so popular, because it has no type definition. You don't need to declare any type for any variable. And that is one very important advantage. And you focus more on the algorithm, less on the type definition. And easy to expressing. Language is used to express yourself. So you want to have some language that become your mentor. But you don't want to have something that is hard to use, hard to learn. That's why people complain about Chinese language. Is the writing system is so complicated, and in English is much easier. You only have 26 letters, and easy to implement. Actually, this is for some economical reasons. We want to have the language to be rolled out fast. Possible to compile to very good code. Is obvious. Backing of powerful sponsors. This depends on the company. Wide dissemination of minimum cost. Okay. The next one, why do we have programming language? Programming language, I would say the most important part is the way of thinking, how you think about how to solve a problem. So the way of thinking is very important. So a language should be useful from the user point of view, and also it should be a way for you to specify what you need and what you want. So a language is you try to program on some virtual machine, and that machine actually is specified by the language. Say, if I have a language like C language, I declare some variable. I never think about the register or some other things. So the language itself, C language itself, give you the idea of, I just need to specify some variable and plus it, minus it, and also I try to print it out. That is the machine I'm thinking about. That's the virtual machine. And the real machine about how the register being transferred, how I fetch the data from memory, that's not my concern. That is how the language hide the hardware from me. That's an abstraction. So the hardware to do without getting down to the bits, that's the purpose of the language. Language from the implementer's point of view. The implementer is the one who developed the language. So whether how you determine certain data type. Say I have a polymorphic method, I need to define which library or which function I would like to call. That is based on the choice of the implementer, not the programmer. So some language also got affected by the implementer or designer of the language, not by the user. So it's kind of like a contract between the programmer and language designer. The art of language design, including the evolution, spatial purpose, personal preference. These all different factors we are talking about right here will determine how a language is being developed. And then express power, easy of use for novice people, ease of implementation, standardization. So some languages are very standardized. Some languages keep changing. For example, like C++ have evolved so many generations, and Fortran also many generations. Some languages like Java have been similar for a long time. And then open source. Whatever language is more open source will have more popularity. More people will use it. And then excellent compilers. Some compilers are very lousy, make you don't want to use it anymore. That is also important for language. And then economic issue, people try to sell it. That's very important. Now we work on why we study programming languages. Right here, we need to choose a language for different application. We have the purpose for system programming. We have purpose for numerical computation or data analysis. We have embedded system. We have symbolic manipulation. We have network computing. And right here, actually modular 3, nobody uses it. And this language nobody use it. This nobody use it. So we know who is the champion, whatever. And this actually this I copied from the textbook, and it is no longer a competitor for Modular 3 or Modular 2. I just list them right here. But to choose a language, you need to know about your application domain. And modern real-world language, right here, I list down different applications. And for server, probably people know about this better. I don't want to spend too much time. Mobile language suite, and the Objective-C for iPhone, Java Android system for Android system, C#, and Visual Studio for Microsoft phone, the Windows phone. This the mobile language. And right here, desktop language. Whoever work on the desktop programs. And because a lot of desktop program is not sold by selling the CD anymore, people just do download. And because of a download, actually mobile system and the desktop system become blurred right now. So it's no longer that much difference. And hardware description language, you have VHDL, Verilog, System C. These different languages are used to define a hardware, say a chip. And they provide you the high-level register transfer level language defined by these different language, and then convert it to gate-level netlist. And gate-level netlist converted to the layout. They call it the database for a layout, and then the layout being done to the mask, the photo mask, to prepare for the mask shop to generate the chips. And the mask is defined in this EDIF. And the program in circuit level, people use SPICE or HSPICE, that's another nodal language to do simulation. So right here, as you can see, the EDA industry has quite many languages as well, but it's not popular for outside people. But anyway, there is a certain domain. If you want to find some job with the knowledge for programming language, it's right there. And Hadoop, MATLAB, R language, Python, Ruby. These are different languages for database and also for numerical analysis, data science. And this XML, this one is JSON, CSS, HTML, JavaScript. These different languages are for markup and data languages. And so we try to, in this course, we try to make it easier to learn new language. Some languages are similar, so I talk about it as a language family. So for example, like a lot of East Asian language are very close to each other, and also Latin language like Italian, Spanish, Portuguese, they are very close. And Eastern language, they share the same kanji system, the CJKV, Chinese, Japanese, Korean, Vietnamese, Sino-Tibetan language. These are close. Their written system are similar, and the Indo-European language are similar. You know, that's people call the language family. Same thing for programming language. We have the C family language. We have the Python family, as I mentioned, and that's the family. If you know about the language family, it's easier for you to learn a new language in that same family. And how can you make better use of whatever language you use? And right here, I don't want to spend too much time on this. And this one, how can you make better use of language you use? Understand the implementation cost. And this is very important because if you want to be a master in certain language, you must know how much time you spend on programming and how much efficiency you gain. Say, if your program is mission critical and you need to finish in a certain turnaround time or latency time, then you cannot afford to miss the target. Say, some website program, you need to make sure that customer get a response within, say, 5 second, 10-second range. You cannot afford it to miss the target. Say you allow a bank a person who go to bank to withdraw or deposit money, and you allow him to wait for 2 minutes. I believe that is too long. So you need to make sure that your language, you know, you do it, you do the program the right way. So actually your program is efficient enough. And as long as how it's called efficient or not efficient, that depends on different application and different domain knowledge. So that it's actually this study of programming language will help you to understand the implementation cost and the efficiency of the program. And also this course will help you to figure out how to do things in language that don't support them explicitly. Say there are certain control structure in Fortran. How can you do it so that you can provide a better organized or readable program? Use command and programmer discipline for control structure, and try to help you to understand how to do programming in certain language without using recursion, something like that. And this one to figure out how to do things in language that doesn't support them explicitly. Okay, and this is a continuation of the previous slides. Lack of name constants enumeration in Fortran. And again, these different things listed down in textbook actually is, I would say, out of date, because this problem already been solved in newer language like Java or C#. They no longer have these problems. Okay, so I will just go over it quickly. And the study of programming language need to answer for yourself. You need to answer these different things when you pick up the language. What is available in the language and what is not available? Say if you are in Java, there is no pointer. You cannot use pointer to do anything. How can you solve the problem without pointer in Java, but doing the same data structure programming that you need in Java? And actually, I will have one example later when we talk about object-oriented programming in Java for using reference as a pointer. And then what is good for the language, what is bad for the language, and what is the use for that language. I think this concludes this part. Let me have a short break. Let me check our Brendan has any question on that. How are you right now? I have a short break and then waiting for his response. Okay, great. You know, sometimes continue to talk more than 1 hour is quite a tough thing to do. Okay, let me continue. Let's go on the lecture suite. Actually, I spent too much time on those simple stuff. I need to pick up now. Otherwise, we cannot finish week 1. We will be here forever. Okay, let me see. I need to jump to now language spectrum. Okay, there are two main category. One is declarative, one is imperative. Imperative means order. You give the order to the machine. So the most popular machine model is Neumann model. We'll talk about this a lot. Actually, this is the main topic we have in this course. And then object-oriented programming. As I said, object-oriented programming is adding another layer on von Neumann machine, so it's actually no difference. Okay, these two are no different. Scripting is a interpreter-based language. So again, this is actually no difference from von Neumann. So von Neumann imperative language is the mainstream for the modern language right now, is in everyday use. So we talk about this declarative language. We have functional language, data flow language, logic-based, constraint-based language. It's called declarative, so it's not like imperative language, statement by statement type. It's declarative, so it's rule type. It's data flow type. It's someone calling someone type. Okay, and this one is not someone calling someone type. The imperative language is one by one type. You finish one statement, you do the next one, and you jump to somewhere. The declarative is different. It's I call you, you call him calls someone else. This is how the declarative type work. I try to use a simple language so you can understand it better. And functional language is by calling some function, apparently. And data flow is you have an origin of the data and flow to somebody else. And we will explain this later for data flow. And logic type, you have rule 1, rule 2, and some fact, and you do a reduction for the rules. Okay, we'll go to the model later. Now, here we talk about the declarative language. Functional programming, you have function A calling function B calling function C, C call D, D call F, and A call E, A call B and E call C, okay, whatever it is the function call. So the program is driven by the function call. And data flow is, if you know about MATLAB, they has a package called Simulink. Okay, you have some data source, maybe an image, then actually you have the list of the files, and then you pick up a certain file, then that file being loaded, read the image in, and then smooth the image, you do some filtering, and then you actually convert it to some white image or something. So the image of file name and image got processed stage by stage without using any order or instruction or statements. That's called data flow model. So data flow from source to sink. That's data flow programming. And the function or the operator being placed in between is called data flow programming. Logic programming, we have Zhang like Jane, Jane like Zhang, and Jack like Jane. Okay, and these are facts. Someone A like B, B like C, C like D, those kind of things are facts. And they are rules. If X like Y and Y like X, then X and Y are friends. If X like Y but Y doesn't like X, then X and Y are not friends. So this left-hand side need to be, if left-hand side want to be true, the right-hand side need to be both true. So this is a rule, the reduction rule or deliberation rule. And the rule need to check the facts. So say I put in a rule, say whether Jack and Jane are friends or not. I try to evaluate this value. Then I will put X right here, that's Jack, Y right here, that's Jane. So whether Jack like Jane or not, yes, this will be, first part will be true. But whether Jane like Jack, Y is Jack, Jane, and X is Jack, that's no, because that doesn't exist in the fact. So the answer for whether Jack and Jane are friends or not, no, they are not. So this is driven by logic reasoning. That's called logic programming. That's how Prolog is working. So this part, we have functional programming, logic programming, data flow programming. These are declarative languages. And right here we have object-oriented programming language. Let me introduce this vanilla programming first. The so-called vanilla programming language is based on the accumulator model. You have the CPU, you have the ALU, you have memory, you have the input-output. This type of machine is called vanilla machine and vanilla programming, if you do programming on it, okay? And then, as I said, these different objects are represented in memory as an object. So this is wrapping up some C language content with some extra object-oriented derivative or language feature that become a C++ language. So C++ language is object-oriented programming because the core is C, but they add some extra layer on it that become an object-oriented programming. But you think differently when you use object-oriented programming because you think about object, you think about the data, you think about the member data and member methods. And that's object-oriented. And that is actually still operating in vanilla one statement by one statement situation. But object-oriented programming can also be executed in a event-driven programming environment that is some object being invoked by other object by some mouse click or some button click or some window interrupt or something. That's called event-driven programming. And event-driven programming can be implemented by maneuver model like in JavaScript situation, because in the website, you cannot have multiple core, you cannot have multiple processor. Instead, you are thinking about the web engine is serial, so you need to use a event loop in JavaScript to implement the event-driven programming in serial programming environment by implementing concurrent programming in event-driven type. So these are related, but somehow they have different programming concept. Scripting language, excuse me, scripting language actually is relying on virtual machine or some interpreter. So some Python code that is a Python script, sometimes people call it, or a Python precompiler module, PYC. They will merge together after the Python script being converted to bytecode, and the bytecode being sent to a Python virtual machine, and then you do the program. And Java is similar, except that Java is all compiled before they send into the virtual machine, the Java virtual machine to run it. But Java 9 is coming maybe this year in June or July timeframe. It will have the interpreter and the shell environment like scripting for Java. So I'm expecting to see it pretty soon, later this year. And right here, we have different programming paradigm. The third thing, it is not mentioned in the textbook, but I would like to point it out, is gaining popularity because of the mobile environment. It's called block programming. If you look at the Snap language or Scratch language, you do programming not in statement by statement. You don't type anything. You just click and drag and drop and try to assemble the language like this. This is called the block programming. So the programming style is totally different. It may be still an imperative language or an event-driven paradigm, but the way you do programming will be different. You do block programming, and each block will perform like an event or like an object. It's different from the maneuver model, but it's based on maneuver model actually on the machine side. But conceptually, the programmer would program totally different from the derivative language, different from the imperative language. Another example is my block. you may have, this is more like a data flow, like Simulink type, MATLAB Simulink type of programming. And as you can see, they have source and sink. So this is actually block programming, but more like data flow model. The third one is MIT My Inventor 2. Of course, there is a certain module called Inventor 1, but now they do like this. It's similar to the Scratch, but they will allow you to build a app in a very short time. It's called My Inventor 2. You can go their website to find out what it is. But these are block programming language. It's graphical design, imperative, data flow, and sometimes rule-based. So it's hard to say which programming model it really belongs to. It can be imperative in Scratch case. It could be data flow type in my block situation. So I couldn't say, I cannot say what it actually belongs to. So I will call it is a block programming paradigm. And the last one, you will see the 3 different ways of doing GCD, the greatest common denominator for A and B. And these are done in C, that is iterative type program. And it's done in OCaml, that is actually a recursive type. You can see this language, excuse me, has some input and then has some return value, and then this value come in and it returns something. That's the return value A, or else you return something by calling a subfunction. So this is functional programming and it's recursive. And in C language, this one is actually a iterative. But we know that C language can also do recursive. So this book example just try to give you some idea of the difference between iterative language and this one is declarative language. It's called functional programming. And Prolog is based on rule and facts, as I mentioned. So these 3 examples try to give you an idea of different way of doing programming. That's the programming spectrum we talk about in this lecture. The next part, we'll talk about this important gentleman. His name is John Newman. I believe he's coming from some noble family. He's very, I cannot say rich, but very noble in some sense. And he is an important figure. Okay, he's still very powerful. People still talk about this Newman machine very much. And the most important thing he invented is the use of memory in digital computers to store both sequence of instruction and data. You would question this. What is the big deal for using memory? And memory is in computer every day that we have right now. So why this guy invent memory is so important? Let me just jump this some description you can read. And iterative, we will talk about this quite a lot. Let's jump to some machine model. Okay, right here. This is the Newman machine. Okay, think about before we have this memory, actually you only have some logic or gates, right? And then you have some register. We call it accumulator in the Newman situation, not register. So you basically have input, you do programming, you do some logic computation, you store back to some register, and you read out. So there is no backup in the memory, and you cannot swap process, and you cannot do stack. You cannot do a lot of things. Your input and output have to come in, processing, get out, come in, processing, get out. So there is no buffering. That's one thing. Second, you cannot store 2 programs or 3 core programs at the same time. Third, there is no step. You cannot do recursion. So this may be only good if you are not a neural machine. You can be only doing some very simple punching of the key, maybe just a calculator or some very easy things that can be done for the electronics. So the introduction of memory make programming so fun and make it possible that you have an operation system being stored in the memory, being able to be called every time to do the service that you needed. That's why this person, Mr. Newman, is so important in computer programming history. And right here, I will give you some automata theory. We have combinational logic, finite state machine, push-down automata, Turing machine. Again, later I will show you why Newman is so important. Let's get started from combinational logic. Okay. The combinational logic is you get some number of bits, you have some data getting out. Okay. Theoretically, this combinational logic can do whatever you have done in modern computer. Say I have a big file of 5 giga and I don't have memory, and I still be able to use my combinational logic to produce the right output format I want to have, maybe 10 terabits. But it is not economical to do that. So combinational logic somehow only good for some decoder design in nowadays. For more complicated computing, you have to do something else. Okay. Then let's hear today we still use combinational logic in different applications. In code converter, we have the coder decoder. Okay. In ALU, we use that for adder, subtractor, comparator, PLD, programming logic devices. In data transmission, we use it for multiplexer, demultiplexer, encoder, decoder. Okay. And then finite state machine. We have, after combinational circuit, we start to have some memory. And this memory is different from the memory we talk about in the Newman machine. This right here actually is some register. So you can record down the number of the states. You can store the states for your machine. And then you will be able to do minimum or more machine for synchronous and asynchronous case. You can have a state transition, jump from one state to the other and get the input, get the output, input in, output out, and you change the state. So you probably have learned some of the finite state machine already, but this give you the state. But in the combinational logic, you don't have state. So this state transition base can make the computing that originally can be done by combinational logic to be much easier because you have some sort of register layer already. But up to here, it's still not a Newman machine. It is improved from combinational logic, but not there yet. And these are the structure for mini and more machine. I don't want to repeat this. Some people took the logic design may already know this, so I will just skip this one. And then nowadays we have Faraday logic machine. It's all based on the rule, the logic design, but they have the grade level for the input. This is not the main topic here. I will skip it. And then you have different programming paradigm using neural network to do image reconstruction. And it used the partial information from different neurons and then gather information to decide whether this one would eventually come to some convergence point and they propagate the knowledge to the different layers. And sometimes this is one way to organize the neuron stage by stage. So the neuron will be able to learn the partial information from the nearby or neighboring neurons and gain some knowledge. So neural network is a way to implement the artificial intelligence, and it is used mostly in image recognition or image restoration or reconstruction. But this is the different programming paradigm that we have from von-Neumann machine, and it is quite popular. Foundry logic, the same thing, is not von-Neumann based. I'm just covering this different programming paradigm right here. And then DNA computing, you have your problem encoded in DNA type, and DNA have 4 different coding, the A, T, C, G, different type, and then you put those different encoder together and then put into the magic bottle and you shake it, and then DNA will be doing the mutation for you, and then you get the data out. And this has been a research topic for quite a while. So for computation, first you need to find out what computing model you want to have. von-Neumann, rule-based, like logic, or Foundry logic, or neural network, or DNA computing. And then you find the programming paradigm and architecture. Say you use Intel Core 7 to implement this, or you may like to have your electronic to implement neural network, or you may have chemical bottle to implement the DNA, something like that. You need to find out your architecture and your machine to implement it. Then you find your programming language. That's how you implement a computation. And in this course, we focus on the programming language, the von-Neumann model, and some of the rule-based model on von-Neumann machine, something like that. That's the focus we have on this course so far, and will be the way we will do for the remaining of the course. Next one is interpretation versus compilation. Let me have a break right here. Let me check the opinion from our Brendan. Are you okay to go over time? Okay, then we will continue. You know, it's an intensive course, so I don't want to finish chapter 1 right here, because we have to make sure that we cover all the topic we have, as long as you don't mind to go over time. I'm sorry, I should go next slides. Okay, I will try to make myself more concentrated, don't talk too much on unrelated topics. Okay, the next one is interpretation versus compilation. The purpose for discussing this is, say we need to choose these 3 languages, C++, Java, Python, right? C++ is pure compilation based. Java is hybrid. This Python is interpreter based. Okay, so only by this factor you have to choose these 3 languages. You will, you have to determine what you want to do. So right now, actually, more of the device level programming or the native, say, machine dependent issue are using C++, because the compilation is more suitable for that. And for Python, we like to be totally machine independent. So even the data type, we don't want to define it. Then this Python language is suitable for conceptual programming like statistic data analysis. And Java is something in between. So Java tries to learn something from Python, and trying to be able to convert it to more machine level. So it's something in between. Okay, let's move on. Right here, let's talk about a pure compilation. C language is pure compilation. So you have a source program, you do compilation, you get the target program that's called from C to machine code or from C to Java code. It's okay that C going to another high-level language is allowed. It's also compilation. So as long as there is a source program, there's a target program, and we convert one language to another, this another maybe is a machine language, maybe it's a assembly language, or maybe it's a high-level language, it's all okay. It's called compilation. As long as it doesn't slow down to wait for your reply or iteratively process your language, that's called pure compilation. So it's okay to compile C to Java. And then now it's pure interpretation. That's script-based interpreter. So Python is one of these. So actually you have source program, you type in something, the interpreter responds to you for something, and then you keep doing that to have the program input being fed into the interpreter, and you get the output. This is called pure interpretation. And then comparison. Interpretation has greater flexibility. You can do whatever you want to do. Actually, at the wrong time, you can change course. You don't have to follow the procedure of your program. Compilation will give you better performance, but once you write down the program, the program will be executed one by one. So interpretation is more flexible, better diagnosis, but performance will be poor compared to compilation. And then hybrid is something like Java language. You have a source program you interpret to, you can translate, or I should say it's a compile to an intermediate program. And then you can use that intermediate program with some input to run in Java virtual machine. This is called hybrid. And virtual machine, first you compile from Java code to some bytecode. Bytecode is intermediate code, but this intermediate code bytecode is different from the intermediate code in compiler. It's different. It's a target language actually. And Java program using the compiler, you have target code, bytecode, and bytecode stored in .class file, and .class file being called from different machine for the Java virtual machine. That's Java interpreter. So the left side is compilation. After the bytecode, it becomes interpretation. So Java is called a hybrid method, but a lot of people still call Java is a compiler-based language because of the front end part, the front stage part. But in fact, it's a virtual machine type. And Scala language actually is based on the Java virtual machine, but they use the compiler of the Scala compile to Java bytecode, and then they can run on Java virtual machine. So this hybrid type paradigm actually gaining popularity, and there are more than 200 languages right now supporting the Java virtual machine. So it's quite important. It's one of the main topics we have right here in this course. So in the beginning, we had a compilation all the way for Java from source code to target machine code, but now we call it just-in-time compilation. That means I compile to bytecode, but that's not machine code. And then when you run it at runtime, I load the bytecode, and then I optimize it, and then do code generation, and then try to find a native environment on the runtime. That's called just-in-time compilation. Okay, that's called just-in-time compilation because the compilation is done at runtime, not at compile time. Okay. You assume that this compilation should all the way from source code to machine code, but just-in-time compilation actually is queue the back end of the compilation at runtime, not the compile time. So compilation does not have to produce machine language. Okay, that's one point I point out. Compilation is a translation from one language to another. Compilation entails semantic understanding of what is being processed. Pre-processing does not. Pre-processing only convert the file format. Okay. The next lecture we are going to cover the pre-processing. Many compiled languages have interpreted pieces, formats in Fortran or C. So this doesn't mean too much. Okay, most use virtual instructions set up operation in BASIC or in Pascal. This virtual instruction is not really popular. Some compiler produce nothing but virtual instructions. This is for hybrid, but Pico is the early version of the hybrid of the virtual machine, and then bytecode by Java, and then Microsoft C++, COM+, for the .NET environment. Now the next thing would be the compilation strategy, mixed compilation and interpretation. And right here, every language may use one or more compilation strategies. So in this lecture, we are talking about how to compile something or interpret something. And I will give some example of which strategy should be used. Okay, preprocessor. I'll try to run through this quick, and then we will see some example. That's making more sense. Preprocessor is to remove comments because comment doesn't make any sense. And then white space later. That's the tab or the return. New line, \n type of letters, or space that's needed, not needed. Group characters into tokens, keyword, identifier, numbers, and symbols. Expand abbreviation in the style of macro assembler. So there might be macro, then you can assemble it. Identify high-level syntactic structure, loop or subroutine. So that's what preprocessor is doing. Let's look at the preprocessor. In C#+, we have the preprocessor, and preprocessor usually talking about the directive. The directive include punch sign include, like actually will be including some source file from other like .h file, and then you actually call some subroutine or function or get access to some external variable. That's the inclusion directive, and that's done in preprocessing. That means that you have to find those call before you do compilation. So the call is being expanded somehow before we do compilation, and that's the purpose for using the preprocessor. And there are also macro definition like define, undefined, and they are conditional compilation derivative, if, else if, and if defined, and if undefined. So these are very useful, especially when you need to set some debugging version or some release version or some development version. Some part you want to compile, some part you don't want to compile. That's the conditional compilation derivative. That's done in preprocessor. So after preprocessor, you pick the right call to do compilation. That's the purpose for preprocessor. Allow you to choose what call to expand and what call not to expand, or what call you would like to repeat many times, and your program will be smaller. After your preprocessor, you will be expanded and then fed into the compiler to generate the object code. And there are some derivative like this. This maybe this will be covered in some of the later chapters. And preprocessors is up to the source code. After that is compilation. The second strategy to be used is library of routines and linking. Okay, in the old day, people develop all code by themselves, but then later they have library, and now we have the foundation class, and then we have studio. A lot of things we have SDK, software development kit. You know, the name keep changing, but it's like a lot of pre-compiled code or pre-developed code from other people. You can link it at the compile time, or you can actually find the code at the runtime by dynamic binding, and that's the use of library of routine and linking. And nowadays people call it dynamic binding or something, but actually this is one compilation strategy to use the library and link. Post-compilation assembly, in the old day when we use C language, you can choose to compile to assembly code. And then we can have C language, we can have Fortran language, we can have assembly language, and then we use assembler to combine them together into machine language. But that's called post-compilation assembly. And the C+ preprocessor conditional compilation that I talk about this in A, that's used for you to choose if there is a certain debug version and some development version. Some of the messages need to be printed out, but you don't want the customer to see it. That's the purpose you set up the conditional directive to help you to make sure that some message doesn't show up in the customer's code. And source-to-source translation, this is C++, and you can come from C++ to a target language, say C. That's the source-to-source translation. And this is not difficult. Let's move on. Bootstrapping. Bootstrapping is complicated. Let's look at the next chart. Okay, this is the UC San Diego Pico system for Pascal language in about 1978. So you have a program, and it's being compiled to machine code. The machine code need to match the machine code on the machine that you want to run. So that actually make the Pascal language not easy to use because you cannot use the library. So later, UCSD developed this Pico. So this S is source code, and T is the target code or the temporary code. You know, something you can use later. So basically, you can have this Pascal. You actually can compare to some Pico, and then Pico and some other Pascal code can be compared to machine code at the same time. So usually this Pico is some sort of library, and Pascal is some sort of the program by some developer. So you can look at this Pico as the early version of the bytecode or early version of intermediate code. So the software can develop by some library builder and Pascal, programmer. But this Pascal language doesn't become popular. It has one major weakness, because this Pico and the Pascal code need to stay in same compilation stage. There's no just-in-time compilation idea at that time. So you need to still link or you need to still translate it to certain machine code, and this machine code cannot be used for different platforms. So you have to stay in one compiler to finish this. You cannot say, like in Java's case, you have the Java code, you have some bytecode, and then you compile your own code, calling some other people's bytecode. Then you run on some machine by the user, maybe on Mac or on Unix or Linux, or maybe on Windows. Those kind of things doesn't need to rely on the same machine or compilation environment. That make the Java successful in early 1990s. And this Pascal code is popular. It's been invented in 1978. Pascal became an educational language in 80s, but 90s it became a zombie. Nobody continue to use it. Nowadays, if you want to find a compiler for Pascal, it's so hard because this is an early prototype for virtual machine, but it is actually not a virtual machine. It's just some successful idea of intermediate code. So this is what it is. It's called bootstrapping. Okay. Now let's have a break right here. The purpose of having this break is I'm going to show you the Python idle. Let me bring up Python. Okay, this is Python. Okay, then the first thing I would like to do is, okay, right here I have this desktop. I have this week. I have this Week1S1. I use a shift and right click and then open the command line right here. Okay. Then right here, let me do this. I do dir. So right here, this window environment itself is a interpreter, and it's actually accepting the Windows script. So what I'm going to do is like I type Python. Okay, the first thing I would like to do is just to type exi.py. Type means to print it. Okay, so by doing this, you will type, it will print out, or you would echo, you would type the content of the file es1.py. The next thing I would like to do is I would say Python es1.py. That's used Python interpreter on the command line to run it. So right here, the program is to define the B, and then you actually define a function show B2. That's a function. And then you call a show B2 that would actually just print out this list for B. So the result that is this. Okay. Now, what I can also do is I just call this Python interpreter. Let me move this up. In this Python interpreter, I can import ex1. So now let me do this show B2. I would do this. I'm sorry. When I load this right here, when I load this, when I import this ex1, I already actually load in the program and run it. So show B2 had already been done. So right here, what I should do is, let me do this. Let me do C equals 1, 2, 3, 4. That's you can call it list or array. Okay, actually it's called list in Python language. And then I give a show C function, and then I type in print C. Okay, I'm sorry. Let me try it one more time. Div show C. You know, I get an error message right away. That's an advantage of the interpreter. But Python has its own definition of the indentation, but I did not did it right. So like this, I define a C function, show C function, and print C. Now I just execute show C function, then you print it out. Okay, that's the function of interpreter. I basically do the programming. When I face this interpreter, I type in a lot of things in there, and the interpreter give me some response. Either I did it right or I did it wrong. But the list, say this C will be stored in the memory in the interpreter. And if I define a new function, and this new function I call it, that would get this data and print it out. So that's the function. That's the functionality of this Python interpreter. Let me exit this. Okay. And another way to do it is, as I show you, in my directory, I directly actually right-click and call this idle program. Let me see right here. In here, I have this Python idle function. In chapter 3, I will teach you how to install Python, and we'll talk about how this can be. You can actually learn how to do Python programming. So don't worry about it. Right now, I'm just trying to show you the feature of a interpreter. So in right here, I bring up this idle is also a shell. So let me define it. B equals 1, 2, right? And then I define show B function. And again, I print B. And now I just do show D. So this Python idle would do the same thing like what I did. And also I can do this in the Python shell. I can open. Let me go to my desktop because my week 1 session 1 directory is right here. I'm going to open, say, let me pick this example 2 now. So my example 2 had this, right? Okay, you will print out hello world. So right here, I can click run module, and then you print out the hello world. So with this idle and the interpreter, I can actually perform similar to a compiler, but it's still a interpreter based. Now let's do another thing. Let's bring up the BlueJ. BlueJ, I would ask you to install it in week 1. Let me open the project. Let me go to desktop. And then our week 1 session 1, there's a BlueJ, let me call it. There's a test program. This test program only called hello world. Okay. Then I compile it and run it. This is one example for compiler based, but it's compiled to intermediate code. And the intermediate code is located in this directory. Right here, you have the test1 class. This one is intermediate code. If we try to open it, you cannot do it because it's not actually visible. And there is a CTest file. You can open it with certain editor. It's written down as this. So the bytecode and the CTest class text file code, they are related. It just makes it smaller for the class codes. It's totally in binary format. The duck class code is the intermediate code in binary format, but CTest file is in text format. Okay, that's intermediate code. But later we will see more example on this intermediate code part. Let me check. Brandon. Okay, are you okay to continue? I can keep going on, but I don't know whether he can go or not. Okay, let me continue. I just tap for everybody. Okay, we finished the just-in-time compilation. We are here. The next one is this interpretation strategy. I show you an example for using the Python interpreter and the DOS interpreter. Okay, the next one is talking about a Python interpreter. Python, you have the source code. That's the one I show you, the ex1.py, that's one example. And it's compiled to a template code called PYC, or you call it Python compiler code. That's a bytecode. And you fed into a Python virtual machine. Actually, this Python virtual machine is an interpreter. And you will never see this .pyc code because this one is not supposed to be seen by it will be removed by Python. So in your directory, you will never see this. But somehow, if you want to keep it, it is possible. And in some commercial product, when they ship Python, they only give you this .pyc code. They don't give you the source code. So the interpreter, if you set the flag right, it will be okay to ship with this PYC code. Okay, so source code compiled to bytecode, bytecode go to interpreter, that's a virtual machine, to be executed. And then this is also another strategy, dynamic just-in-time compilation. I mentioned this already. I will skip it, but C# language will produce .NET Intermediate code, CIL, also Visual Basic and some other languages. Java just-in-time compilation, I mentioned this already. I need to move on faster. And microcode. Microcode is from the assembly language instruction set. It is not implemented in the hardware, and it runs like an interpreter. So say I have an instruction. I do not run it directly. So the instruction being get from your memory and then put into a certain decoder, and that decoder actually will get some microcode. So microcode is like a smaller program under the assembly level. There's still some program. So this level is called another level of instruction set, actually translation. We call it microcode. And instruction interpreter is written in low-level instruction, and sometimes it's actually in firmware or microcode in circuit design actually. So that's what used in the microprocessor design. And this one is showing you a Nibbler 4-bit CPU, and that CPU has this instruction to microcode. So your instruction right here, jump, conditional jump, something, okay, jump compare, I see, should be something like that. Jump equals 0, jump not equals 0, add I, add M. This instruction will be translated to these different microcode, whether to do it or not doing it. This is another layer of interpretation. Compiler exists for some interpreter languages, but they aren't pure. Okay, that's like Python. Selective compilation of compilable pieces and extra sophisticated preprocessing of remaining source. interpretation of part of code, at least, is still necessary for the reason above. So even though the Python had the PYC, some of the code still need to be there for interpretation purpose. So this lecture is covering interpretation. It's just tell you for all of the interpretation languages, some interpretation still needed, even though you had a pre-compilation or some .pyc code, but it will not be complete if you are using the interpreter based. Unconventional compiler, these are different. Silicon compiler, I mentioned about this for the hardware design. Text formatting, that would help you to accept some file and reformat it to a different file format. And query language processor like SQL, so that people can use the language to search the database for a library, something like that. These are unconventional compilers. Now I'm going to talk about programming environment. This is the old-fashioned tool, still used in Linux. So you have editor, printer. This actually is a formatter to help you to make the print more beautiful. And then we have preprocessor, especially for macro, for C++, and this different thing. We have debugger, we have style checker, lint purify, we have module management for Mac, and we have virtual control, revision control system, SCCS, assembler, we have linker, and then loader, decoder, and runner. Okay, anyway, this still used in Linux, and this is the old-fashioned of doing compilation. And nowadays, the programming environment have improved. We can have a source editor, and the source editor right now, like in Notepad++, that will help you to highlight the program structures, like while loop, the keywords, the parentheses, whether it's matching right or wrong. This source code editor has the language dependent information extraction. So this file will extract the language dependent feature and would highlight it. That's the purpose for this source code editor. We have Notepad, and the blanket I just show you. Actually, I have a blanket. And later I'll teach you how to install the blanket as well. It's included in one video we have. And there's a subtext or subline text, something like that, different source editor. And the Mac program is the program builder. It's used for C, C++, and some like Fortran, the older language. And the Mac file actually allows you to manage when some file being affected or being updated, then Mac file will automatically call to make sure those touched unit will be recompiled or relinked. Otherwise, those untouched, say we have an application, some of the modules say this file 2 is not updated, then when we do Mac, it will be omitted. They will just recompile those parts being affected by the updates. That's the purpose for the Mac program. And virtual control. Virtual control is very important because when there's a group of people, actually we will allow different version. Say there's a development version, there's a production version. So there's a certain developer want to update, say, a version 3, but version 2 or version 1 may be in production. So there's a person who want to use that production version to ship. He can still update and then ship it. But the one developing a newer version may be adding some more feature that is not needed by the older version. So you keep shipping it, you keep maintaining it, but the newer version, some developer can still add in some function into it. That's the purpose for version control. And some maybe debug version, some production version, some release version, some in maintenance mode, never change. And IDE, integrated development environment. In this course, I heavily suggest this Eclipse system because it almost support every language you can see here. And some NetBeans is big, but NetBeans is going down. And then there are certain different IDE, but doesn't support all of them. And some IDE like IntelliJ IDEA, it become much more popular now. Even some of the developer prefer this, but it's more commercial. You need to pay to get it. And Visual Studio is used mostly for Microsoft environment. Android for the Android development platform. Xcode more for the iPhone environment, iPhone, iPad environment. So these are different popular IDE right now. You can pick if you need to develop a certain software in certain platform. So the next thing is the overview of compiler phases. There are 6 phases. I try to run it fast because chapter 2 is totally on compiler design, the first 2-3 phases. So I won't spend too much time right here because we are going to talk about this in the next session. And this automata, I just give it. The most important part is this phases of compilation. There are 6 phases. The first phase is lexical analysis. So basically, your source program come in, you will generate a token. And what is token? Token is actually a string. Token is actually a symbol, a string. So it basically makes sure that your source program being reformatted into a string of tokens. And that token is actually a string, a basic language word unit that being used for parser to analyze its syntactical meaning and later for semantical meaning. Syntactical means the program structure. Semantical meaning means that whether the type or the content of the data matching the type or not. And then the next one is if the structure is correct and then content makes sense, then we move on to the next stage for intermediate code generation. Now, at this time, maybe the bytecode already been generated, and then the compilation or optimization maybe in the just-in-time compiler. And maybe this is actually a target source code, something like that. Or maybe you need to continue to work on the machine-dependent issue or code generation and code optimization. So these are the 6 stages. The top 3, we call it the front end. And the bottom 3, we call it the back end. And front end deal with the source. Back end deal with the machine-dependent issue. So that's the way we divide it. And symbol table goes through is the most important data structure used to support these different stages. And then the first stage is called lexical analysis. It just do scanning to divide the program into tokens. That's the whole purpose. And at this stage, we use the DFA, deterministic finite automata, to help it. And the definition of this will be in chapter 2. We won't go into detail right here. And deterministic finite state machine, finite automata is like this. So basically, this deterministic automata is including some state, some input language, and some state transition. That's it. And there is no ambiguity for the state transition. That's why we call it deterministic finite automata. So basically, you have input, you have state, you have state transition. That's the definition of state machine. Okay. The only difference is this one is deterministic. It's not non-deterministic. Deterministic means that I get some certain input, I will get into some fixed state. There is nothing like I get some input, but I may go to two different states. That will not happen in DFA. And parsing is to use the push-down automata. And push-down automata, actually, the only difference that push-down automata has with the PSA, the deterministic finite state machine, it is including the stack. With the help of stack, you can build a tree, you can do recursion. So that's what parsing is used. And parsing, the purpose of parsing is to, because the previous stage we do the scanning. Let me go back to the previous stage. The previous stage divide the program into tokens, right? So you have certain symbol, you have main, you have parentheses, you have argument, or you have integer int. Those are called tokens. And now we need to use the parser to analyze the program structure. So we would like to make sure a certain tokens in combination will become a statement, or you will become an expression, or you will become a program. That's the purpose of having the parser. So push-down automata, as I mentioned, the only difference between the push-down automata and finite state machine is the state control, state transition delta is the same, state is the same, the input is the same. The only addition for push-down automata is this stack. With the stack, you will have the first in, last out. You will have recursion. You will build a tree structure. So this will save the number of states. As I mentioned, let's move back. Let's go back. Whatever can be done by finite state machine can all be done by combination logic. Whatever can be done by push automata can also be done by combination logic. But you may use terabit input, terabit output. That doesn't make sense. So finite state machine help to save some data, and then will minimize the combinational logic. Push-down automata will help to do the tree structure or recursive call much easier with the help of state. So the sense, so this push-down automata again will minimize the design much more. Again, actually, this push-down automata is useful to help parsing. Parsing need to build the program structure into a grammar tree. So that's why we need that. And this will be covered in chapter 2. And then the next one is when we finish the tree structure, then we need to analyze actually. So at that time, when we finish the parsing, we already know there is a certain statement, right? But now we need to do semantic analysis. Maybe there is a equals B plus C, but B is a, say it can be a integer, and then D may be a, I'm sorry, A equals B plus C. B may be an integer, and C may be a double. Say right here, maybe some language doesn't allow it to be summed together. I'm just making this up. But semantic analysis is to detect this. If there's some sort of type mismatching, it will detect that and report it. That's the purpose for reporting, the purpose for semantic analysis. So you actually use the semantic analysis to do something that you cannot determine or you don't know by just looking at its structures. It's more than structure. It's analyzing the language in the number of value sense, not in the structural sense. So the compiler can actually do what is called static semantic analysis or dynamic. Static analysis means you actually analyze it in compile time. Anything called static is in compile time. Anything called dynamic is in runtime. So some language would allow the error to be found at the runtime. You use exception or error. That's the runtime. So some semantic analysis is done in runtime. And the next stage is the intermediate form. As I mentioned, this could be an intermediate call or some of the register transfer level language, so that it already determined what variable need to be do what operation. Like A equals B, you need to assign A as an integer, B as an integer, and then C as a double, and then A need to be a double. You need to reserve those registers together and know about what operation need to be done. And then we call this as a intermediate format or intermediate form, but it may or may not be compatible with your target machine. So there is certain, maybe in virtual machine, there is certain just-in-time compilation still need to be done for the backends. Okay, and some language, the intermediate form can be directly translated to machine code, just like C, C++. Actually, the intermediate form, the output already been the assembly or object code. And then the last two phases for call optimization and call generation, conceptually is easy. We will just move on. And then machine-specific optimization, you based on your machine to optimize your call, and then you generate a simple table to help you to handle the different phases. And actually, this simple table will be constructed early in your token stage. You have the token, you have the later string converted into token, and token built into simple table. So this it will be built early in this, and that simple table will be used for different stages in your compilation process. So now this is the overview part 2 for compiler design. Let's move on faster. The front end has 3 stages: converted from character string to token, token to parsing tree to some intermediate form. Okay, that's the front end. And then you can work out, you can add more input. That depends on your machine structure, whether it's a Java virtual machine or it's a Python virtual machine, or you generated the target code directly. Not right here. Let's look at one example. This is a C program. This is called a character string. It's the GCD program we saw in the previous lecture. Okay, let's move on. And this is called a token format. So int is 1 token, main is 1 token, parenthesis is 1 token, this right parenthesis is another token, bracket is 1 token. So you basically actually generate these different tokens. That is, you build up a table, and then this will be put somewhere in the table, main in somewhere in the simple table. This is the result for the lexical analysis. And the next stage would use the context-free grammar for the C language to do parsing, and then it will build. So this is context-free grammar. Say this one is to parse the number, a number will have a sign. It's plus, it will go here. It's minus, it will go here. Okay, and then if it has the whole number part, we go to here and then repeat for several digits. Otherwise, if it is only a fraction number, you go here for 0. And then after you finish the whole number, you come here, you look at the period, the decimal point, and then you may not have decimal point. Go back, go down. Here's the whole number. If you have the fractional part, you come here, repeat several digits. And if it is in scientific format, you go into here. So this actually will help you to interpret. It will help you to build verify whether a number is a valid number or not. Similarly for program, block, or declaration. So context-free grammar, BNF, Baker's normal form or Baker's norm form, is used to make sure that your input string or your tokens are in the right format. And this is actually used for lexical analysis for the first stage. And later you can use the context-free grammar for the program structure. So context-free grammar would be like this. Let me look at this. A statement is a compound statement, and compound statement will have the block with the block list, block item list, and optional and bracket. Okay, and in this we'll have the block item list, brand item list. We'll continue to have several different blocks, and then the end. So this is how we will explain this in chapter 2. Okay, so don't feel frustrated if you don't understand this. Basically, the context-free grammar is to help you to make sure that the program structure after the token is following some language format. Okay, so the GCD will be built into such a grammar tree. Okay, so complicated anyway, just for its GCD program. So it's something like this. So, okay, let's move on. And then that tree will be built into a certain AST abstract syntax tree. And the symbol table is like this. And the program will be defined like this. And right here, these two different symbols, are not in C format. We call it the intermediate form. And this is ready to be used in later backend stage to generate code. Now we are moving on to the last lecture for this session. So right here, in this course, we basically will teach you the development of a programming language. So we have a computing model, Neumann machine, lambda calculus, logic, neural network, and DNA. I mentioned about this in computation model. And we go into programming paradigm. You have Neumann programming, object-oriented programming, script programming, block programming, pair programming. We have functional programming, logic programming, data flow programming, event-driven programming, signal slot, whatever. And then these will go into language development. Language development, we have keyword type, composite type, program structure, if then else, we have the subroutine, we have objects. Okay, so from the model to paradigm to language design, and then finally we need to go to the compiler design. So the compiler design basic part are this. The front end and back end, you may have a virtual machine, or you go into back end design. And actually, you have this to support. This different language structure need to be handled by the compiler. And then this language you need to support this different programming paradigm. And the back end, will be machine-dependent issue. So right here, we have let me summarize this chapter. We have maneuver model. We have the electronic design for the combination logic. We have lambda calculus for functional programming. We have logic programming paradigm or value logic. We have neural network, that's different programming paradigm. We have DNA computing. We can have optical computing. We can also have mechanical computer for abacus or some of the early computer. And right here show you the programming paradigm available on Earth. So it's so complicated, different language. Pascal, C, Snowball, Prolog, Java, OCaml. So you probably spend some time on this, and let me know if you don't get it somehow. It's so complicated. And runtime environment. Actually, right here, I'm going to teach you. For example, if you learn some certain language, you started from the basic structure programming, like C equivalent part, and then we move on to object-oriented programming in C double plus equivalent. So right here in Java language, you have the loop, subroutine, you have selection, if then else, and then you move on to second part, that's Java 2, is object-oriented programming, that's C double plus equivalent. Then you move on to GUI programming, file structure, exception, numerical package, geometrical package, string, data collection, data structure, concurrency programming, generic programming, database, chart plotting, network, unit test. These are called development kit, or sometimes called it the API. So if you want to learn a language, you pick up from the essential part, the if then else structure, and then you package into the object-oriented programming. And the object-oriented programming, because of the object, is used to manage different database, libraries, or the development kit. So this is the essential knowledge you need to have to know about this. So when you learn the language, you follow the path like here. And if you are early to learn the programming, you should go all the way through by only one language. And finally, you go to the design framework, client-server programming model, and then you pick up the Design Studio, compiler, IDE, API, framework, and etc. And then we complete the chapter 1 right here. I spent quite a lot of time on this chapter because I go into introduction for myself, and I actually maybe waste people a lot of time, but I'm sorry, but I try to cover everything we can. Let me check with if Brendan is okay. Okay, and for those people who actually watch the recorded session, you can always email me or become a friend on my Facebook. I welcome you to actually post any message at any time. Okay, let me bring up my Facebook. This is not my Facebook for the student. Let me try another one. Okay, this is my Facebook for my student. First, let me go to my, okay, right here. If you type Facebook and then Dr. Eric Chou, you will come to my technical Facebook. The previous one on the Chrome is not for students. And this one is for my students. So you can become a friend and you can post me message or any request. Of course, you can send me email through the Blackboard as well. I will answer any question you have. And also, right here, you can come to this Facebook group Louis programming language. I would make announcement here as well, and you can join here as a member for this group, and you can chat with your fellow friend on this course as well if you have some problem. And I'll try to check this, an email and maybe phone call is welcome as well. Let me know if you have any question. So if not, we will finish this session. So let me ask him if he has any suggestion. I would like to thank you, Brendan, to stay so long with me on this session. Yeah, sure. Next time I'll try to be shorter, but I try to give quite enough information, as much information as possible. Again, because this is an 8-week, actually it's an 8-week course. I don't want people to come here and decide this is useless course and you do not learn anything from here. And so I go over time. Hope everybody can excuse me. Okay, thank you. Bye.